Hey physics fans, today we're going to continue our discussion on AC circuits by discussing the three circuit elements that you're going to see in this course when tackling AC circuits. The resistor, capacitor, and inductor. We've discussed the resistor in series with the alternating current power supply already, but just to review, some of the main conclusions that came out of that was that by applying the definition of resistance and starting with an expression for a time-varying potential, we were able to conclude that the current through a resistor is equal to the current's amplitude times sine omega t. Now what you should notice is that if we compare the two trigonometric expressions for potential and current, you'll see there's no phase angle difference between the two, which is why when I plot the potential and current with respect to time, I see that the peaks line up and the troughs line up, and because they do that, it is in phase. There's no phase difference between the two. Now, when I look at a capacitor, I'm going to tackle that in much the same way that I did the resistor. I'm going to consider that I have a capacitor in series with a time-varying potential, right, which I've written here. I'm also going to consider two equations from our PRC. The first is that charge is equal to capacitance times potential, and that current is the derivative of charge. By applying some math, I'm going to have an expression for the current through the capacitor. Now I have an expression for current with respect to time through the capacitor. But when I'm comparing that to potential, it is often helpful to ensure that the trigonometric expression between the two equations is the same. And what I'm going to do that is apply a trig identity. Now I have an expression for current with respect to time and potential with respect to time. And you'll notice that unlike with the resistor, now there is a phase angle difference between the current through the capacitor and the potential across the capacitor. That phase difference is actually pi over 2, which when we plot the potential with respect to time versus the current with respect to time, there is a pi over 2 difference between the peaks for both plots. What we refer to this as is that the current through the capacitor leads the potential across the capacitor. Now, when we're discussing AC circuits, we run into a term called reactance, right, which is the opposition of a capacitor to a change in current, specifically for a capacitor in this case. Our expression for that reactance is chi sub c is equal to 1 divided by omega times c, or the angular frequency times the capacitance. Lastly, we'll discuss an inductor in series with an alternating current power supply. We're going to express the potential as a function of time, very similar to how we had before, which is the amplitude of the potential is equal to sine omega t. We're going to use two concepts, one equation and one principle, to relate the current to the potential. The first is that we know that when current passes through an inductor, there is an EMF that opposes the current, and that is negative the inductance times the change in current with respect to time. And the principle we're going to use is Kirchhoff's loop rule. By combining those, we achieve an expression for the current through the inductor. Similar to what we did with the capacitor, we're going to apply a trig identity to ensure that we have the same trigonometric function for current and potential. By applying this trig function here, I now have an expression for current through the inductor in terms of sine. You'll notice, similar to the capacitor, I now have a phase angle, but instead of plus pi over 2, it is now minus pi over 2. So when I'm plotting that, I'm actually going to have what's referred to as a lag. In the case of an inductor in series with an alternating current potential, the current through the inductor lags by pi over 2 from the potential across that inductor. And because this is an AC circuit, there is a reactance associated with the inductor. The inductive reactance is chi sub L is equal to the angular frequency times the inductance. And this reactance is the opposition of the inductor to a change in current. That's all for our discussion on AC circuits today. Feel free to ask your instructor questions.